All right, welcome everyone to this training on how to design inverter gadgets. We'll be having an introduction on how to design an inverter system. So there are basic things you need to know about inverter before you think of designing an inverter. There are some key things that I would love to highlight you, and I will please emphasize that you pay careful attention, because these are some kind of errors some of us have made while designing inverters, and we are seeing the precautions and the problems we're facing today. So please, you follow me carefully as I will guide you through on the following. Now, this is what we're going to be looking at on this today's class. We'll be checking what an inverter is. We'll be checking the kinds of inverter signals. We'll be checking the types of inverters. Then block diagram with detailed explanation. A block diagram of an inverter with detailed explanation. How does it looks like? What are the chambers that are inside the inverters? These are things also we'll be looking at. Then the main IC or MCUs, that is integrated circuit or microcontroller unit, that will be used for this design. Then components that will be used and their functions in relation to the circuit. Any component that is in this circuit, we will explain it and its function, what it's doing in that circuit, so that you also will know how to fit in. Then we'll be doing sizing for inverters. That is, how many MOSFET do you need? For example, 1000 watt. And what is the size of transformer you need? That is, if you are doing a transformer based inverter, you will know how what is the size of the transformer you will need for a particular capacity of inverter. Then protection system like low battery cutoff, over voltage, reverse polarity, and short circuit, then overload. These are the battery full system too. These are the protections also we'll be checking on this system, how to design them and how to apply each and every one of them. Then the input voltage. When designing an inverter, you need to, what will determine your input voltage now will then determine the capacity of the inverter also is in response to the input voltage and vice versa. Now let's take an example of a 1 kVA inverter, which is most 12 volt system. Now if you are going for a 2 kV, we then recommend a 24 volt system, so that it will lessen the work in the transformer based system. But if it is transformerless work with a very high frequency systems, so some of them don't literally need to go in respect to such kind of voltage at a wide range of wattage. Then the charging current also, we will be checking on each inverter what is the maximum charging current we'll be using and the minimum. So these are the things we'll be checking on the inverter systems completely, and after then we'll see what we'll do next. So let's go to the next. Now, what is an inverter? I know many of us are into the system, so we know what an inverter is. But for those who are just new, or for those who are just coming up, or for those who are just attending this class for the first time, we said an inverter is a device that converts direct current to alternating current via different kinds of conversions process. Now there are several kind of ways to get an inverter. There are several kind of ways. We can use a single transistor oscillator, we can use Wayne bridge oscillator, we can use operational amplifiers, we can use a pulse width ICs like the one we'll be using here, and also other microcontrollers. So there are different ways of designing inverters, but the conversion. But this is the direct current. Here is the kind of current your battery produce. Your battery produce this first current you see here. Your battery produce this first current that you are seeing here, direct current. So when your battery is being charged, this is the kind of current it gives out, a direct current. Then what your inverter, after going through the inverter and the processes, it gives out the alternating current. Now under this alternating current, there are key things we'll be considering. There are key things we'll be considering. Now, the number one thing is the kind of inverter signals. The kind of inverter signals. Now, we have three inverter signals listed on this particular diagram you are seeing here. The first one, we have the square wave inverter. The second one, we have the sine wave inverter, and the third one, we have the modified sine wave inverter. Now let me take time to explain this carefully so that many of us will not be confused. The first one, which is the square wave inverter, if you can see, it has a rectangular wave kind of signal. Now this kind of signal gives your inverter a noisy sound, especially when using transformers, low frequency transformers. You will hear the inverter making a kind of a body sound like zzz, a kind of a buzzy sound on the inverter system. Why? Because the signal is not smooth. Now, the side effect of such kind of inverter is when they are connected to inductive loads. Inductive load or resistive load, let's say for example, like your fan, your standing fan or your ceiling fan, you will notice that the fan will begin to make some kind of noise when connected to such kind of inverters. So sorry, so on such kind of systems, you get to understand that your UPS, like some common UPS, they are square wave. Some of them are then modified sine wave. Now this modified sine wave, sorry I'm jumping to the third one. This modified sine wave is just an adjustment of the square wave inverter. It's just an adjustment. They just make some kind of modification. That is what is giving that modified sine wave. So it reduces the noise from the system. It completely reduces the noise from the system. So now you will observe that the noise will be there, but it will not be that much. So when you connect your inductive load like fans, it will make the noise, but you won't clearly hear it will be that deep. Then when you go to the sine wave now, that is the kind of signal your grid, we call it NEPA here in Nigeria, but for other countries the national grid, when it is being restored, you get the pure sine wave signal. So that signal, as you can see from the diagram, is very smooth. So that is the best recommended kind of inverter you will need for your appliances, though it is cost effective. That is why it is more expensive more than other inverters, because of the kind of signal it is producing. So in a nutshell, sine wave is more recommended, but square wave and modified sine wave are easier to design and they are commonly gotten in the market. Now we have under the types of inverters, we have the low frequency inverters. Now when you hear low frequency inverters, that is most at times low frequency inverters are inverters that uses transformers. That is step up transformers. If it is 12 volt, it steps 12 volts to 220. If it is 24 volt, it steps 24 volt to 220. If it is 48 and continuously. So this kind of inverters uses 50 or 60 hertz frequency. It uses 50 or 60 hertz frequency. That is for the low frequency inverters. Most of them are transformer based inverters. So they uses a 50 or 60 hertz frequency speed of switching to generate their output. Now the high low frequency inverters, why I use the high low as a term to describe this inverter is it has two chambers inside. It has a DC to DC converter. When we go there, I will explain further. It has a high frequency chamber and it has a low frequency chamber inside of that transformerless inverters. Those one does not use transformers, they use a couple of inductors, boost and buck converters to generate their own kind of energy. Then the hybrid inverter is not different from the two inverters I've listed above. The hybrid inverter's function is just added. The function is just added. Now, the hybrid inverters we have, under hybrid inverters, we still have low frequency and we have high low frequencies. Now, under the hybrid inverters, why it is called hybrid is because it is having an added component or a added chamber inside, which is responsible for charging your inverter system when you connected your solar system or your PV array. So when your PV array is connected, when your inverter has an inbuilt charger inside, it is said to be hybrid, irrespective if the charge controller inside is PWM or MPPT, which is maximum power point tracking, or pulse width modulation charge controller. So that is what makes your inverter a hybrid inverter. The presence of your charge controller inbuilt inside the inverter, it makes it a hybrid inverter. Now here are the hybrid inverters, not because it's different from other inverters, but just the one more thing is added into it, which is the MPPT or PWM, as I've explained. They are built-in. It is same as other inverters, both transformer and transformerless inverters. Now if you check this diagram carefully, you will notice that the solar panel is connected directly to the inverter. The national grid is connected directly to the inverter, and the battery is connected. So the charge controller is built inside of this inverter system, and this inverter system is transformerless. Most of them are transformerless. Most of hybrid inverters, only few are transformer based, but most of them are transformerless. Now the advantage, when I get to that transformerless, I will explain the advantages and disadvantages. Now the low frequency inverters, as you can see from this image on your screen, this kind of inverter by default goes with low frequency, by default goes with 50 or 60 Hz, as I've explained earlier, and gives out 220-volt output using a transformer. Now the transformer you're seeing here, most of like these ones, they are called UI transformers. UI transformers. So if you check carefully, there is the MOSFET board beneath and the driver board on top. Now once this inverter is connected to a battery, it does not go through any other conversion. It goes directly to the driver board. The driver drives the MOSFET, and the inverter gives out output. Sorry please for the call that just interrupted. So these are for low frequency inverters. Now the disadvantage of this low frequency inverter is the no load current. Most of the times you see the no load current very high. When there is no load attached to it, you notice the no load current is very high. That is all the disadvantage of this low frequency inverter over transformerless inverter. That is for transformer based inverters. That is the only disadvantage you will have on this system. Then for high frequency inverter, if you check carefully, there is no transformer inside. You only have a couple of inductors. Now if you check very closely, this kind of inverters use both high and low internal configuration. For example, the input voltage now from your 12-volt battery, the input voltage that is coming from your 12-volt battery needs to be boosted to 330 to 400 volt. That is on DC. Now if you check closely in this inverter, there are two cards hanging on the top. If you check very closely, there is one behind and there is one closer here to you. So the one behind is responsible for boosting this 12 volt into 330 volt to 400 volt. Then the second one is responsible for generating a signal at 50 hertz to get your H bridge that will give out that 220 using 4 MOSFET. That is H bridge, 4 MOSFET. Now the one behind generates a frequency of 150 kilohertz. Some generate 100, some generate 150, depends on the company, but mostly it is 150 kilowatt. So such kind of inverters are easily damaged due to the kind of circuitry it uses. This one uses a MOSFET for its output, while these transformer based systems uses transformer for output, but the transformerless uses MOSFET for their output. So that is one of the difference, and that is one of the side effect. When there is a problem, the MOSFET will directly just burn. But when it is for the transformer base, most at times it will equally affect the MOSFET too and bypasses the transformer. But when there is a very good protection, your inverter will be secured and it will shut down. But the disadvantage of this one, as I've said, is if there is any short circuit protection, directly most at times it affects the MOSFET system. So this is one of the disadvantages of this inverter. But one of the advantage again, it is a very lightweight inverter and it is affordable. It is more cheaper than the transformer based inverter. Now, one thing I want us to consider on these inverters is these high frequency inverters you are seeing, they have some kind of little harmonic distortion. Their signal is not as pure as low frequency signals. It is sine wave, but there are some kind of ripples, unlike the transformer based inverters. Now this is the block diagram of a transformer based inverter. From your left hand, you will see a 50 or 60 hertz square wave oscillator. Now the oscillator is a particular chamber responsible for generating signals. The oscillator you are seeing here, its own function is to generate signal alone. That is either square wave signal, it can be square wave, it can be sine wave, it can be modified sine wave. Now this signal generation is the ICs or the microcontroller is responsible for generating that the signals in response to the frequency that is there, 50 or 60 hertz. Now the signal that is generated will then be feed to the MOSFET driver. It will be feed to the, as you can see the arrow, it will be feed to the MOSFET driver. Now your transformer now will be connected to the MOSFET driver, whether H bridge or center tap transformers. It will be connected to the MOSFET drivers. So now as it is switching, it will be switching in between, the cycle will be continue in between the transformers and then produce output. Now if you can see the arrow of the battery is connected to the oscillator. The oscillator gets energy from the battery to generate low signals that will feed the MOSFET gates. Thereby the MOSFET switching within the cycle of the transformer core, then generating output. I will explain that briefly when we start building the inverter system. These are just introductions that every one of us need to know, so that when we go further you won't get confused. Now the block diagram of a transformerless inverter system. Yes. Now if you check carefully, you see the input supply, that is the battery. The input supply, that is the battery. Then the number 2, you see power supply for the converter. Power supply for the converter. Now this transformerless inverter, as you can see, has some chambers, as I've told you earlier. The battery, the light that is coming from your battery need to be boosted. Why? Because the output will be given out not using a transformer, but it will be using the output will be using a MOSFET, 4 MOSFET H bridge. I will also explain that in the circuit as we go on. 4 MOSFET on H bridge, that is what the circuit the transformerless inverter used to give out its output. So now from number 1, check your number 1 closely. You see the voltage supply, that is the battery. The input capacitors, these ones are responsible for filtering and maintaining the inverter, while the DC to DC converter switches boost this input voltage, the 12 volt here. Now the number 5, check your number 5, you see the DC converter with control circuit board. It is responsible for boosting the inverter circuit. So it will boost your 12 volt to 330 volt to 400 volt within that range. So now it will boost this battery voltage, so that when the H bridge is supplied with that 440 volt or 400 volt or 330 volt, it will switch in between. Now there will be a feedback that will go back to the DC to the DC to DC power supply, so that it will maintain the particular voltage until the battery drops down. so that if it is 220 to maintain 220. Then if it is for Americans or German which uses for Americans that use 110, so that will maintain 110, and for Germany 250 to maintain 250. Now if you check, here is the oscillator. That is after the DC to DC converter, then we have the oscillator, which is responsible for switching the voltage provided from the DC to DC converter. Now if you check the tested input inductor, the inductor, if you know, a normal boost converter comes with an inductor. So the oscillator now will switch the high voltage coming from the DC to DC converter and give it to the load, as you can see in the number 6. So this is a very simple diagram of the transformerless inverter system. So you can see it is a bit complex, unlike the transformer based inverter. Now these are the hybrid inverters. For the hybrid, you have your solar panels connected, as you can see there. Then the regulator battery charger. So the regulator battery charger is the charge controller that is built in inside the inverter system. That is the regulator battery charger. Now the regulator battery charger can be an MPPT, as I've said, it can be PWM. So it is connected and attached to the inverter board, that when it senses the solar panel, it continues charging. But most inverters come with MPPT, and it is recommended that when designing such kind of system, you use an MPPT. Though we'll be teaching you how to design an MPPT controller too, as at the long run. So after the regulatory battery charger, which is the MPPT controller, that is what is embedded in the inverter system. Then the inverter circuit. Then after it connects to it sends to the inverter circuit. Then the switching device, which is your MOSFET, then it goes to your transformer and give out your output. So as I've said, the hybrid inverter, the only thing added is these first two chambers. There is this second chamber, sorry, the regulatory battery charger. Instead of buying a charge controller and mount it on your wall, it's just attached into the inverter system, and it's called a hybrid inverter. It is not different from other inverters. Now these are the basically ICs that we'll be using on this project. They are very simple to use. That is why I want to use them, so that for those who are not conversant, with such kind of ICs or such kind of typical component when it comes to electronics, can be able to design this system. Now basically we'll be using the following integrated circuit and microcontroller modules, which is Arduino specifically. Now you can take beneath, you can see SG3524. SG3524. Now these are IC, is an analog IC. It provides square wave signal though, but I will teach you how to modify this square wave signal to a modified sine wave signal and lower the noise coming from this IC. So we'll be using this IC to produce an inverter. We'll be using it to produce charge controllers. So this IC is very essential, as you can see, and I'll be guiding you through on how to use it to design these systems. We will be using it also to make battery chargers, 3-step battery charging from bulk, float and absorption, using this same IC. So as you can see, it's a multi-purpose IC that every one of us will throw attention to. So after the video, I'll be dropping the data sheets. The data sheet is responsible to tell you details on how this IC works and everything you need to know about the IC. Now the first board from my left is the Arduino board. The Arduino board is an MT80 mega 328 or 324 microcontroller. You can just send a program to it and you simulate and make your inverter. So if I'm teaching you using Arduino, I will make sure I provide the code for you. So please don't panic. I will make sure the code will be provided after the program or the teaching. I will make sure that the code is provided and the circuit diagram will be provided for every one of you for free. You don't need to pay for that. Then the EGS002 is the main board for sine wave. Is the main board we will be using. Now this EGS has so many features, but it has limitations because you cannot use this EGS to make charging. But I will teach you how to manipulate this EGS and use it for any capacity of inverter, even if it is 10 kVA, 20 kVA, 1 kVA, 5 kVA, 3 kVA. All of them I will teach you how to manipulate these systems and make your inverters and also your charging systems. Now please thank you for watching this video. We are done for today's video. We'll meet on the next. Please make sure you press the subscribe button and like, and also please make sure you share this video and press the notification icon. We'll meet on the next video. Thank you.